Welcome to our ePro Wraps Up the Best of VI in 25. We're really excited to have everyone here today. We have a great lineup of speakers and we have a unique format. With the format that we're going to cover today is every speaker gets 10 minutes. There'll be a 10-minute Q&A at the end of the talks, and there's a little Q&A button on your Zoom where you can submit your questions. The comments have been disabled for this webinar. The more time I take in introductions, the more time it takes away from our speakers. But if you are interested in learning more about ePro products that are used to mitigate VI, please visit our website. You can reach out to us after this webinar, and we'll be happy to assist you. The speakers today are well-known experts in vapor intrusion mitigation, and we'll be covering a lot of highly detailed topics in a very short amount of time. The first set of presentations, or the first set of presenters, are Sugrita Reines and Andrew Campbell. They'll be covering the documents that have been created by the Association of Vapor Intrusion Professionals that detail the proper design, installation, and OM&M of vapor intrusion mitigation systems. So without further ado, here's Sugrita and Andy.
Thank you for that introduction, Peter. And so Andy Campbell and I will jointly, in our allotted 10 minutes here, give you a very quick overview of the two of our presentations at the AVIP conference this year, and it covers the topic of risk and performance objectives and metrics. All right, so just want to emphasize that this is a super fast, few minutes summary of a multi-part workshop, and so we don't expect everyone to, absorb all the details, but we just want to have a quick, give you a quick overview, and most importantly, introduce you to a document, one of a series of documents that was published by the Association of Vapor Intrusion Professionals, specifically the design roadmap, and then mention a couple of the other ones, and also want to emphasize that we're presenting basically one way to do this, and it's not meant to be an exclusive, like this is how you have to do it. It's just one way to approach design. There may be, and I'm sure are, others that work well, but this is just to provide sort of the beginnings of a basis for design. All right, so we'll talk a little bit about risk objectives, define those, risk metrics, and then setting the numeric performance objectives, introduce you very quickly to the calculations, not going through them in too much detail, and then also touch on performance verification. And here on this slide, you can see the cover for this best practices guidelines that AVIP put together, and you can see the assistance from a lot of folks from a lot of different companies collaborated to put this document together. And so it does represent sort of an overview of best practices from a number of practitioners in the industry. And also, just to mention, there's a companion guidance document on operation and maintenance of these systems, and yet a third document also on construction quality assurance. And I would say all of those are equally important, but this one just focuses on the design. So what are risk objectives? The way we like to think about this is that the objectives are, of course, numerical, and generally there are two that we look at from a human toxicology standpoint. One is the excess cancer risk, and generally EPA and other agencies, look at it as a range of 10 to the minus 4 to 10 to the minus 6, so 1 in a million odds of developing a cancer that you might not otherwise develop in your lifetime, and the hazard index, which should be less than 1. And of course, important to always remember that if you have multiple constituents of concern, you need to sum all of those together. All right, and to give just an example here of applying the guidelines and going through the calculations, you need to know a lot of information before you get started. You need to have some idea of your concrete properties. We've included in our presentation just a couple of examples that we feel are sort of decent, if you will, values to assume to start with. You may have other, for example, specialty concretes, different permeability. So things to keep in mind. These are just examples. Gravel layer, we've assumed a certain thickness, a certain permeability, a certain porosity. Permeability, porosity probably hold true most of the time, but you might have a 6-inch gravel layer or a 12-inch gravel layer. So again, these are just examples for the calculations that Andy's going to go to in more detail. Your constituents of concern, of course, soil properties, depth of water, right? You might have a dry installation, or you might have, 5 feet below ground surface, encounter groundwater table. So these are important things to know going into the design. And of course, building dimensions. And one of the key parameters that's sometimes tough to nail down early on is, for example, the typical ceiling height. And then, so here's just again plan elevation for a building, and calculated the cumulative risk and hazard index for this example. And again, Andy will go into more detail in his segment. And so what we need to do is we need to translate these risk metrics of excess cancer and hazard index into an acceptable indoor air concentration for each of the constituents of concern. And I think a lot of folks are familiar with the concept of an attenuation factor, which is simply the ratio of the concentration in indoor air to the concentration in soil gas. And very simple graphic here. So you have concentration in soil gas, which then presumably attenuates, dilutes a little bit in the gravel layer, and then your COCs need to get through your vapor mitigation system, the membrane as well, and then it encounters the concrete. So there's multiple, right, steps along the way where the concentrations can be attenuated. But the sort of the gross attenuation captures all of that. So indoor air concentration to soil gas. And one of the things that we wanted to get across in our presentation is that risk drives performance. So in the previous graphic, you could see you have whatever concentration you have of your COCs and soil gas, and your performance objectives for the vapor intrusion mitigation system are set by what you need to get to for your concentrations in indoor air. So again, what is the performance for your membrane? What's the performance for that you can assume for concrete, and so on. So we're just looking at how well does the system need to perform in order to mitigate the risk that's presented by your COCs present in soil gas on your site. And so with that, I'll hand it over to Andy to go into the further details on this.
We are here to reduce risk. Your performance metric is generally whatever attenuation factor alpha you use to replace the EPA's default value of 0.03. Engineering controls like vapor barriers, that's one example. They give you a smaller alpha value. That's better, and it allows you to calculate a better risk metric with that additional protection. You can also have an attenuation factor for something like a ventilation system. But in that case, your calculations may or may not build in the 0.03 for the floor slab. It just depends on where your point of control is. Here's how you would calculate the attenuation factor for a vapor barrier using field data. Radon is a useful surrogate for doing this, and Glenn Tofani will talk more about that later on today. But before you ever get to the field, you will want to know how a vapor barrier should perform and what it will do. And we can calculate safety factors for some of these failure mechanisms that you see here. The reason we can't calculate for all of these failure mechanisms is because we don't know how large a membrane defect will be. That's this side of the grid. Those defects typically occur during construction, so you don't know yet, but we can calculate how big a defect can't be, and we call that the critical defect size. We don't have time to discuss all the math involved here, so we encourage you to obtain the presentation slides from the AVIP 2025 Wednesday workshop, where we go into more detail. Okay, now about performance metrics for subslab depressurization. In the workshop, Cheryl Carey and Elizabeth Wang of Catalyst Environmental Solutions explained that when you apply the concept of flux to VIMS, two kinds of flux cause VOC migration into the indoor environment. Advective flux is the transport of a substance through the bulk movement of the fluid that the substance lives in. That's these arrows. They act over an area. It's the physical transport of air with VOCs flowing from the subslab environment into indoor air. Pressure gradients drive advective flux. And then there's diffusive flux, the transport of VOCs down a concentration gradient. And in an environment of high concentration of a compound, and that's these orange dots you see below the slab, diffusion causes the compound to move into areas of lower concentration. And that's the other dots you now see above the slab. Diffusive transport occurs independent of pressure gradients or the net movement of matter. Michael Nemeth will elaborate on how that works in concrete, also later today. But to be 100% effective, an SSDS needs to overcome advective and diffusive flux. You need to know what amount of negative pressure is necessary to overwhelm all of that. And that's what these downward arrows represent. They're a counterflux, if you will. And if you can do it, you sever the exposure pathway. For severed exposure pathways, the attenuation factor becomes 0. Or with SSDS, you might end up just attenuating the vapors. You can calculate that too, but we don't have time for the math. So again, we recommend checking out the workshop materials from AVIP 2025. Alternatively, many regulators have their own performance metrics for this. It could be 1 Pascal of differential vacuum, 4 Pascals, or 10. Also, at the 2024 AVIP conference, Yogi Panda introduced a great spreadsheet model for predicting subslab vacuums. This is one way to determine if you're likely to achieve your performance metric throughout a new building's subslab airspace. Or you could instead do a pressure field extension test for an existing building. And David Hanley will speak about those today. And we don't have enough time to calculate attenuation by subslab ventilation, but the AVIP 2025 workshop also covered that. And Yogi Panda will present some calculation methods about that today. Finally, in the workshop, Jonathan Sanders explains some methods of calculating indoor air ventilation. I threw in some more equations I've found helpful. Many of these parameters are actually available in the Johnson and Ettinger model guidance. So that's it for us, and we'll now move on to the next series. Thank you all.
Cartoon here on the top right corner where you have the vapors off-gassing from groundwater and soil, potentially diffusing upward toward a building slab, can then come through the cracks through advection. And I think this is what we understand well. This is our basic understanding of diffusion by advection. You can see the vapors in the cartoon spewing through the cracks. But there is another pathway, which is diffusion through the microscopic pores of the slab. That, as Andrew alluded to as well, is driven by concentration gradient, not pressure. So that, even though it may not be as rapid as an advection through a crack, it does happen over the full bulk of a large slab, and it also happens potentially 24/7 and 365 days a year because the concentration gradient usually doesn't stop like pressure gradient might. So this is the pad sampler that we developed. It's really pretty simple little device. It's basically, think of a Band-Aid and replace the cotton part of the Band-Aid with activated carbon. And then the adhesive of the Band-Aid, the little plastic strip, replace that with an aluminum piece of tape, which about the size of a quarter. You just lay the little adsorptive layer down and then cover it with the aluminum tape. And then as the vapors diffuse through the slab, they get intercepted and absorbed by the activated carbon. At which point we can leave those deployed for a few days up to a couple weeks, depending on source strength, and then send those off to Beacon, who's developed a way to thermally desorb these wafers like they do their other passive sampling devices, and can detect down to 10 nanograms onto one of these pads. So this is the little pad sampler. So I'm going to skip to diffusion theory right now so we can talk a little bit about theoretical calculation of flux through a slab. So diffusion through concrete basically follows fixed first law of diffusion, which is shown here in this equation. It's a differential equation, but it's actually a pretty simple one. And it gets even simpler when you realize that indoor air is basically negligible compared to the subslab, typically concentration-wise. So then the fixed first law really reduces to a simple four-term equation where the flux is equal to an effective diffusion coefficient times the concentration beneath the slab divided by the slab thickness. It's pretty straightforward, but the nut to crack here is, what is the diffusion coefficient that we use for calculating theoretical amount of diffusion through a concrete slab if we know the subslab source strength? Well, what we started digging around, we found that the Johnson and Edinger model is actually a pretty good theoretical basis for this. There's an equation that's part of the J&E model for diffusion. You could use this for soil, but you can also use it for concrete. And if you just use the default parameters that are provided in the EPA Visual Workbook for the chemical properties, and then go to the literature for some values for the air and water-filled porosity of concrete that we found. You plug all that into the equation, and you come up with a diffusion coefficient for concrete of about 1.1 times 10 to the minus 4. And what's really interesting is this equation for soil, which we use to calculate diffusion through soil with the J&E model regularly. The default parameters for soil come up with a diffusion coefficient that's only 15 times more than this. So, we don't think of soil as being a good barrier to diffusion. And if cement's only 15 times less permeable, then I don't know if it's exactly going to be a good barrier either. But we'll see some data here in a minute. So to apply this theory, we looked at a good large warehouse building where we had a good robust data set beneath the slab. You can see all of these triangles here are passive subslab samplers, Beacon samplers that we install by drilling through the slab. The slab is big. It's over 100,000 square feet in size, and robust too. It's pretty thick, almost 10 inches thick on average. So we use this data set and that diffusion coefficient I just showed you, and we calculated, well, what's the flux through this building? And so taking each one of those points and then dividing the area around it by a Thiessen polygon, so then we can multiply each concentration point by its respective area, sum them up, and we can get the overall predicted flux through this slab. And when we do that, using that simplified fixed law, we got about 250,000 micrograms per hour flux into this building slab based on that robust subslab data set for subslab. So that seems like a pretty big number, 250,000 micrograms per hour when we measure things in micrograms per cubic meter, usually in indoor air. So we'll see how that comes out later in the presentation. But for flux, really, we want it on a per square meter basis. So when you divide this by the total building footprint, you get that the flux that we measure, or theoretical flux into this building, was 23.4 micrograms per square meter per hour. So how does that compare to what we did when we put the pads down to actually measure the flux and compare to that number? So what we did was we installed essentially 4 pads at 14 different locations in the building, and you could see the squares that represent where those pads got installed on the slab. There were 2 areas where we did grids of 3 by 3 and a 1 foot square to look at variability within that small area. And then we averaged that grid down to 1 point, and that's what we applied in each one of these, area A and area B. So with these 14 points then, again with the Thiessen polygons to divide up the area, sum it all up, we got a flux of 225,000 micrograms per hour. So this is measured flux now through the pads, which was quite similar to the flux I showed you earlier. And then if you divide that by the area of the building again, the per square meter flux was 21 micrograms per square meter per hour, which was remarkably close to the Fick's law calculation. So, I mean, what that says is, well, we used that diffusion coefficient from J&E worked really well and came out to be a good representation with theoretical flux of what was actually measured. And another interesting thing you can do, if you know the flux in through the floor of a building, you can calculate the predicted indoor air concentration if you know the air exchange rate of the building and the building geometry. So using this equation here and that flux result of 21 that we measured, we calculate, given the air exchange rate that we measured using a blower door, a 40 was our predicted indoor air concentration from the flux through the slab that we measured. And we collected 2 indoor air samples during the pad's deployment. And when you average those 2 samples, the average air in the building was 39. So what this is saying is that the flux, the diffusion that we measured through the slab actually counted for all of the indoor air in this building based on our assessment. So diffusion for this warehouse in particular appears to be predominantly where the mass is coming into the building. I mean, it does have some cracks and gaps, but I think, you know, they're fairly negligible, and they were not significant relative to diffusion. So overall conclusions, you can't overlook diffusion. You really got to take a close look at it. Depending on your building, it might be more significant than you might think. The little pads were quite effective at measuring the flux, and it does appear that they're measuring what we expect to come through. And with a mitigation system, you know, like Andrew mentioned, if negative pressure may not be the only thing you need to mitigate a system. You might need to flush out underneath the slab to break that concentration gradient. And you could use pads as a tool to before and after you do a mitigation design to see effectiveness. So with that, I'll turn it over.
Awesome. Thank you very much, Michael. For those of you that don't know Glenn and know our products, he created the smoke test. He also created low profile venting, which I don't believe he sees a penny of royalties on that. Don't get any ideas, Glenn. But nonetheless, I'm very happy to have him. And he is going to be talking about diffusion testing through membranes, as well as some of the QA/QC or system verification testing that he presented earlier at AVIP back in October. So take it away, Glenn.
Thanks for the introduction, Peter. I assume everybody can see my screen. I'll take that as a yes. So today I'm going to quickly talk about three different types of QA/QC testing for vapor barriers. I'll start with testing to evaluate chemical compatibility and transmission characteristics of the membranes. Then I'll touch upon quickly smoke testing. And last but not least, I'll talk about post-installation performance testing to establish soil gas to indoor air attenuation rates for the membranes. First topic, chemical compatibility and transmission rates. We've been measuring both diffusive and convective transmission across membranes since the 1980s, and have had tests running continuously actually since the 1980s in some cases. This is the typical test setup that you see here. We'll have a container, two halves, a solution of water and a VOC in the bottom container separated by a membrane, and then the upper container is connected to a series of activated carbon filters. So as the VOCs diffuse across the membrane are transported by pressure differential, which we can set up across the membrane, they're captured by the filters, and we can measure the rate of transmission and quantify that rate. It's a typical test setup. We've had to use larger and larger test containers over the years as the membranes have gotten to be better and more restrictive. This is a typical result, excuse me, that we like to see. Data points, falling on a straight line in a linear fashion. Our minimum test period, usually for this type of testing, is 120 days. We've had samples that have been running for years. What we don't want to see is, as time goes on, higher transmission rates, which tells us the membrane is degrading. So again, Peters for ePro has a lot of data and can provide this. I would imagine anyone who wants to make sure the membrane is going to have suitable engineering characteristics so you can calculate risk assessment values. These are compounds we've tested, concentrations, and measured diffusion coefficients. The concentrations that we test these at are usually extremely high, in the millions of micrograms per cubic meter. So it's a very aggressive chemical compatibility testing environment. Installation QA/QC testing, these are all standard protocols. One of those is smoke testing, which is pretty critical. Typical smoke testing apparatus, non-toxic smoke like you might see at a concert venue, and a blower to pass the smoke through the vent piping and underneath the membrane. This is a 24-year-old photo taken during the early years of this type of testing, which started in the 1990s. Then and today, we typically lift the membrane off the subgrade during smoke testing, not typically as much as is shown here. This is somewhat exaggerated, but it's beneficial to do that to make sure we're getting smoke under the membrane everywhere. And it also relieves thermal stresses that tend to build up during the installation process due to temperature variations between night and day. So we found that to be very, very helpful. Before we started smoke testing membranes, installations of this size in a typical residence, we would inspect thoroughly and be quite confident that they were intact without any leaks. And then when we started smoke testing them, we would find 10, 15, 20 leaks in something this size, things that you wouldn't otherwise see. So it's pretty critical to run the smoke tests. Just the process of doing that over the years has helped us reduce the number of leaks that we would otherwise have. The third and one of the most critical types of testing I'll talk about is post-installation performance testing. And the attenuation rate, the soil gas to indoor air attenuation rate for a barrier system is dependent upon both the characteristics of the membrane that you're using and the other components of that system, the ventilation components, and to a large extent, it's dependent upon the quality of the installation. You can take a good membrane and basically ruin it if it's not installed properly. The way we quantify the performance of a membrane is with soil gas to indoor air attenuation rate. which is basically the reciprocal of the attenuation factor that Andrew was talking about. I like to use the rate because it's an integer value rather than a fraction. And it's just defined as whatever the concentration of a particular compound of interest is in the soil gas, divided by that concentration in the indoor air, and we subtract the outdoor air concentration because we're really just interested in what's getting across the barrier to the indoor air. We don't want to what's in the outdoor air to count against us. What we found that the VOC source concentrations at many sites are too low for us to measure the attenuation rate of a barrier using VOC data. And another problem in using VOC data for this measurement is that we've got a lot of contaminants on the interior of the buildings from construction materials and other things. So the compounds that are present in the soil gas are often present on the interior of the buildings already, especially with newer construction. And the third issue, in an urban area, we've got fuel hydrocarbons, and we've got off-gassing from disinfection byproducts that we typically find in indoor air, and it's hard to tell what might be from soil gas and what's not. So because of that, we typically measure the attenuation rate of a vapor barrier using radon gas as a surrogate for VOCs. I would say in less than 2 or 3% of the projects we have are we able to measure an attenuation rate using VOCs. It's a very small number because the attenuation rates for these barriers are very, very high, and we typically can't find detectable levels of VOCs in the indoor air. That's the problem. Radon's a naturally occurring radioactive gas. There are 39 different isotopes. There are a couple that are most relevant. Radon-222, which is just called radon, is primarily what we're measuring. It's got the longest half-life of any of the isotopes at 3.8 days. Another isotope that's relevant for other reasons when we're tracing leaks or trying to find them is thoron. It's got about a 1 minute half-life. And I should point out the source compounds that generate radon gas have half-lives that are in the billions of years. So radon concentrations in the ground tend to be very stable because of that. Radon map of the United States, we found even in areas where the radon, soil gas radon levels are supposed to be low, we've got high enough levels to use radon as a surrogate. A lot of different detectors are available to measure radon concentration, some of them inexpensive, a couple $100, some of them more expensive. Some of these devices can distinguish between the different isotopes of radon, which can be useful. We found even these less expensive devices in the $200 range yield results that are comparable with the more expensive equipment. What we typically do, we'll have a gas probe beneath the barrier, and we'll measure the radon concentration in that probe. We'll measure it in the indoor air, and we'll measure it in the outdoor air concurrently over a minimum of a 24-hour period. Typical gas probe connections, we usually terminate them in the foundation stem wall. Typical results, soil gas levels up here, around 150, 200 picocuries per liter, indoor, outdoor air down here. And we measure the barometric pressure, and have a dropping barometric pressure curve like this is ideal because it tries to force VOCs to the indoor air. And for this data, we calculate an attenuation rate of just over 6,000. It's not unusual to find attenuation rates with a good installation of 10,000, 20,000, even 30,000, which compares to the 33, default attenuation rate, which is used by the state of California. So you can get very high levels. This is another test result, the passive system then being turned active on the right. One of the questions we're typically asked by regulators, okay, we can determine what the attenuation rate is at the time of construction. How do we know that's going to last? How do we know the barrier is not going to deteriorate? How do you know a homeowner's not going to jackhammer a hole in the floor slab of their home? And one of the ways to determine that, we've got a number of projects where we've installed these relatively inexpensive $200 monitors as part of the VIM system, and they will continuously detect and record radon levels. And we can download that data without entering the building as long as we're in proximity. Typical testing results, this red squiggly line is the indoor air radon level measured by one of those devices over time. It's a multi-year period. The green line is what we measured at the time the barrier was installed. And then we've got the barometric pressure up here. So we know our soil gas radon level is constant. So if we don't see a significant deviation of the indoor air radon level from that base concentration, we know we still have the same or a very similar attenuation rate. We can also look at the barometric pressure response and see if we're getting inflow through primarily diffusion or primarily convective flow. And
all right. Well, I'm going to talk about how to, well, thanks, Peter. I'm going to talk about how to use modeling effectively to determine the critical parameters for designing a passive venting system. The same thing can be used for active venting, but today my focus is passive venting. So passive venting systems can be represented by these two schematics mainly. One without ventilator turbine assistance and the one with ventilator turbines. The one on the left works with stack effect, which Andrew has actually dived in quite a bit into. Critical design parameters for a sub-slab ventilation system consists of radius of venting influence. That is how far apart we need to be placing the vent laterals, and for effective venting of the entire space that is between the two vent laterals, and then projected airflow in the vent riser, how much air we expect, the vented air we expect to go through the vent riser, and then vent riser sizing, how big the vent riser need to be, and ventilator turbine sizing. In the case of when we are using a ventilator assisted passive venting system, we want to know what size of that ventilator turbine we need to be installing. Again, today for the passive venting system, I'm just talking about the venting system design, not the vapor barrier design per se, which is an integral part of a passive venting system. So here are the factors that affect the vent lateral spacing. The lateral spacing is directly proportional to pneumatic conductivity of the aggregate layer. That means the higher the permeability of the aggregate layer, the higher or the farther away the vent laterals can be spaced. And it is inversely proportional to native soil conductivity. This is something most often we don't pay as much attention to, which needs to be paid attention to, is that the tighter the native soil, the farther away can be the spacing, and then the more conductive the native soil is, the closer needs to be spacing. And then lateral spacing is directly proportional to the induced vacuum. So through the vent riser, whether we're using we're using stack effect or we are using a ventilator turbine, we are essentially inducing a vacuum to the subslab environment. And that the higher the vacuum we are inducing, or we are able to induce, the farther away we can space out these laterals. Traditional approach has been for the design of passive venting system has been pretty much we have been spacing them 50 feet apart. And where is that coming from? It's coming from basically the guidance that I could find, at least provided by EPRO and ITRC. EPRO says 50 feet spacing. ITRC says maximum 50 feet you can space them out. But I could not find any published engineering basis available for these guidance. So the problem statement for this is that venting effectiveness with vent lateral spacing of 50 feet is uncertain, because we do not know, if we space out at 50 feet, whether the entire space between the two vent laterals are going to be actually vented out or not. Smoke testing, sometimes we do smoke testing to, post installation smoke testing to see the venting, but it's really no indicator of venting effectiveness. But all it says is that the vented out space is continuous. That is continuity of the space between the two laterals. And the laterals themselves. So, and the need for a tool based on engineering principles. So therefore, there is a need to develop a tool based on engineering principles that we can rely on in designing these venting, spacing of vent laterals. So this is a schematic showing basically the airflow through subslab. One of the things to understand is that all air comes from the atmosphere, and then the arrow in the middle that you see pointing up is basically the location of the vent riser, and there is this aggregate layer providing the permeable, acting as the permeable layer for that venting. And so all air comes from atmosphere and then basically goes around the foundation, ultimately enters the permeable layer and gets vented out. And most of the airflow that we are talking about in venting is really shallow airflow, not deep. We are not getting air from deep underground to be vented out. It's all coming from the atmosphere, going around the foundation and entering the traveling through the vent laterals and entering the vent riser. So the schematic that I presented can be mathematically described by a differential equation for basically know that the idea is not to present the differential equation or how the differential equation can be arrived at, but the idea is know that it can be mathematically described. The vacuum at every point away from the vent riser can be described mathematically for that schematic. So for that differential equation, there exists a solution. Actually, Digley in the field of groundwater has come up with a solution to that form of equation, and that's what I have adapted here. Is that for distance, as you go further away from the vent riser, at some point the induced vacuum will go to zero. And then knowing that boundary condition at the far away and at the vent riser, you can come up with a solution. And this is what Digley solution. This is the famous Digley solution, that vacuum can be expressed as a function of distance. That means at any distance you can describe this vacuum, knowing the flow or the extraction rate at the vent riser. So using this equation, you can fit this into a spreadsheet and come up with basically degenerate system curves. That's a relationship between vacuum at any distance and then the airflow and the radius of influence. That means you can set a threshold for your threshold vacuum for your radius of influence, and you can come up with radius of influence. For passive venting system, I set the threshold to be 0.001. For active venting system, it's state dependent. In Michigan, we set it at 0.02 inches of water column. So for the following assumptions are used in this model is that airflow in the aggregate layer is laminar and Darcian. Aggregate layer is homogeneous and isotropic, and a certain quantity cannot exceed this the value of 3. Now we can come up with the vacuum induced by a ventilator turbine using a simple equation, and then apply that to a so apply both. So what you're looking at is a situation where we have an existing slab and we have this vent, these 3 points where we have vent risers to vent out the subslab, existing subslab, and then we have a new construction, if you will, that is basically a cutoff trench filled with Asto 57 stone, which is a very coarse stone, and then we are venting out that space as well. So that kind of serves as a new construction type of scenario. So compare, and then using that simple equation, came up with that the predicted vacuum induced by the ventilator turbine is 0.04 inches of water column, and then you can come up with system curves, and then for using the Diglee solution, and then for 0.04 inches of vacuum, we selected ROI of 3.6 for existing slab, and then airflow rate of 1.8 CFM. And then for the new construction, which is the back trench, cutoff trench, we got an ROI of 20 feet and an airflow rate of 36 CFM predicted by the model. And then when we compared model predicted to the actual measured after installation, we find that vacuum, this is for the subslab, existing slab. So model had predicted 0.04 inches of vacuum, and then we measured it as any measurement varied anywhere from 0.003 to 0.016 inches of water column vacuum. And then air extraction rate, model had predicted 5.4, measure was anywhere between 1.5 to 12 CFM depending on wind speed. Model prediction was for 4 mile per wind speed, which is pretty good in the middle of the value. And then ROI model predicted 3.6. We came up with the actual measure is somewhere near 3.4. And then for the cutoff trench, the model predicted 0.04 inches of vacuum, and then maximum recorded was 0.01 inches of water column vacuum. Air extraction rate of 36, maximum recorded of 29, and then ROI of 20 feet, and then we got more than 15 feet of ROI. So which is pretty good agreement with the model predictions. Takeaways are effective vent-lateral spacing are not one size fits all. So you need to you can't just use 50 feet of spacing in every situation. Diglee solution can be modeled into a spreadsheet to develop system curves, and then modeling is successfully used to provide an engineering basis for vent-lateral spacing and ventilator sizing in this case.
David Hanley. He is with David Hanley Environmental. He comes prior years of experience at Geosyntec, and he is another panelist that has a lot of extensive experience in mitigation design as well as implementation. And he is going to talk to us about pressure field extension testing. So he was also part of the AVIP conference. As a plug for AVIP, you see a number of these presentations. If you want to learn about the best of what's going on in VI in a very concentrated, highly informative environment, that is the conference to attend. So, David, handing it over to you.
Thanks very much, Peter. So this presentation was on pressure field extension testing, specifically in mitigation systems on new construction buildings. So we looked at data that we've collected at more than 50 new construction buildings with mitigation systems where we've performed this pressure field extension testing, and broke down the data in different ways to look at it and see what conclusions we could draw and use that information to be able to improve VIM's design in the future as far as performance and efficiency. So some background on what pressure field extension testing is. This is a type of testing that's used to verify that a venting system can get influence throughout an entire subslab. After the subslab venting piping is installed within usually a gravel layer, and there's a barrier over top, and then a slab is poured, we'll go in and put a vacuum on the VIMS riser pipes and take measurements of the vacuum influence in the subslab at different distances away at test ports through the slab. We'll use that data to confirm that the system can be effective and provide vacuum influence throughout the slab, and also to look for things like inconsistencies and issues with the venting system. So this testing can be performed both for active systems that are planned to be active and also for passive systems to be able to give data to confirm that the system could be effective if it ever became active in the future, and to be able to appropriately size a fan to put on those risers. So this testing is a required component of the ANSI ARST CC1000 design standard, which is the design standard that we use to design our mitigation systems. It's also recommended for new construction buildings to be performed as part of the VI best practices roadmap that Andrew discussed earlier and was released earlier this year. Just a couple photos next showing the typical setup for pressure field extension testing. We've got a riser coming out of the slab, and then that's connected to a manifold where we've got a vacuum gauge to be able to measure the applied vacuum, port to measure airflow within the manifold so we can calculate, it measures air speed so we can calculate the airflow rate, a few valves to be able to control the airflow and the applied vacuum, and then our fan to be able to apply the vacuum. And then finally here, a test port on the right where we take the vacuum measurements at very low levels down to 0.001 inches of water column. So the data set that we evaluated for this consisted of systems that we performed testing on during the past 3 years. This included 55 new construction buildings, 932 data points were collected from 164 risers, more than 300 test ports. So I want to acknowledge this photo shows my colleague Joe Gentlecore. He's the one who collected most of this data, which was quite a bit. Before we dig into the data, just an example of what we're looking at as far as a VIMS layout. So this is a design for an apartment building with 2 risers, one here, one over here. The pink dashed line represents collection piping in the subslab. The green line are solid pipes that go across footers. The footers are the red dashed lines here. And then we've got test ports that are our purple triangles. So we measure the distance for those test ports to the riser. And also note in cases where we're going across a footer that can affect the vacuum influence. So we'll take a look at that as well. Here's all the data just plotted on a graph with distance from the riser on the x-axis, and then the vacuum reading at the test port on the y-axis. Not especially helpful to look at it in this way because we test at different vacuum levels, applied vacuum levels. At each riser, we might test at several different levels to be able to see changes in vacuum influence. So we can normalize this data by taking the vacuum influence measured at the test port and dividing it by the vacuum that was applied at the riser. So that tells us the retained vacuum on a scale from 0 to 1 versus distance. So if we normalize the data in this way, it allows us to break it down and more easily compare different tests that were done. So in the full presentation, we gave a lot of data that was presented and gave a variety of things that we looked at. And I'm just going to go into highlights without getting too deep into the data here. But the first was looking at variability in results for 10 different buildings that were basically identical designs, construction, same materials, same contractor. We expected to see that pressure field extension would look very similar between the 10 buildings, but this was probably the most surprising result, is that we found that it wasn't. There was a wide variability. Pressure field extension was acceptable within each building, but some buildings had much higher, stronger vacuum farther away than others. So we don't have a great answer as to why, but I think some theories, just differences in construction and the way these were actually built. The moisture that can get into the sub-slab, I think has a big role, as well as the construction of the test ports. I think sometimes those can be jammed into the subbase or have water in them that can affect the results. Second, we looked at the effect of footers, or no, sorry, of the gas permeable layer, the material that's used. Typically, you see a gravel. We do at least 4 inches of washed stone. In some of these buildings, we had a geocomposite drainage mat, like a dimple board shown in the lower right. So that forms a small void space that can be used as an alternative to gravel. What we found there is the gravel had better performance in terms of vacuum extension, which wasn't a surprise because it has a larger void space compared to the dimple board. Finally, we looked at the effect of footers and how those reduce the vacuum. If you've got a test port on the opposite side of a footer from your riser and there's no piping in between them, then obviously we would expect to see a decrease in vacuum across that footer because there's a break in the gravel layer, and that's exactly what we saw. So to varying degrees, there were differences there in the amount of reduction that we saw across the footer. In some cases, there's some vacuum extension across footers, but it's a significant reduction. So just wrapping up key findings that we saw. Number one, construction variability. Between 10 identical buildings, we saw big differences in the amount of vacuum propagation. Number two, the effect of the gas permeable layer material. One takeaway here is when we design systems with drainage mats instead of gravel, I think we'll probably decide to use tighter spacing in the risers than we might otherwise. Number three, the effects on footers, breaks in the gas permeable layer had a significant drop in vacuum across those. So when we're designing these systems, we account for that, making sure that we have pipes through footers and are providing vacuum influence to each isolated area of the subslab.
First question is for Andrew Campbell and Sagrita, and it's a bit of a loaded one. The question is, where did the 0.03 come from? So I know there's probably a long answer, but I think it might be helpful for people to understand where that 0.03 attenuation factor came from.
You want to do this one, Sagrita?
Sure. Hi, everyone. So I think most people just use the 0.03 number because it is the official regulatory, if you will, number developed by EPA ages ago based on some field data. And many of us, especially California practitioners, have a lot of heartburn around that 0.03 number. And would like to use something very different. And of course, it especially does not apply for structures that have an actual mitigation system. So we have a lot of issues with that 0.03 number, but we often use it as a, if you will, an extremely overly conservative starting point for any calculations. And some of our local regulators basically tell us run it with 0.03 and then run it again with 0.001. And then really use the 0.001 calculations as a point of departure. So anyway, that's a long answer to that question.
Yeah, and I feel like we could do a whole hour on 0.03, right? So thank you. So Michael's presentation, as you might suspect, got a lot of various questions. Maybe we can point people in the right direction. Has this been published anywhere, Michael, where people could do a little bit more, learn a little bit more?
Yeah, it was published. The whole case study was published last year in Advances in Water Resources. So I'll provide that article to anybody if they just email me. I can shoot them a copy.
Excellent. All right, that would be good. There were a lot of questions about it. I don't want to totally go through it, but there's a couple questions I found interesting. Did you factor in the adhesive from the aluminum tape as a potential source for vapors?
Yeah, we did some testing early on with that. Found that there was no detections of at least what we were looking for, primarily TCE, PC, things like that.
Okay. Next on to Glenn. Well, I guess, yeah, can you talk about if there are any concerns with regarding seasonal installations of vapor mitigation systems? Like, should we hold off in the summer, winter, below freezing days? Are there any kind of seasonal concerns that you have when installing mitigation systems?
There are. I mean, anyone that's been out on a hot day and installed a membrane, whether it's a sheet product, HDPE, or spray applied, and it's 80, 90 degrees and the sun's beating down on it. And it looks fine at the end of the day. You may see a few wrinkles in it, but it'll look pretty normal. If you were to come back out, if it's a cool night, cool or cold night, it's not unusual, go from a hot summer day, in California, to a night where it's in the 50s or low 60s. It's not unusual to come out and see that same membrane and it is tight as a drum, to the point where you may have pulled apart some seams or pulled it off of some of the attachment points on the footings. So these membrane materials, whether it's a sheet product or whether it's spray applied, they do change. They have fairly high coefficients of linear expansion, and if you're installing them on a hot day in particular, you need to have some intentional wrinkles in them. And one thing I'll just mention on a side note regarding the 0.03 that Sagrita, I thought, explained well. I think that EPA study that served as a basis for that came out in 1994, and it involved EPA looking at a number of buildings and measuring attenuation rates. And there were a large number of those buildings that had basements, and the average age of the buildings that they looked at was approximately, it was a construction date approximately of 1930. So they were not looking at modern slab on grade buildings. They were looking at older, highly weathered, I guess would be the kind term, buildings to establish that. And that was intended to be a very conservative attenuation rate, even for those buildings. And one other thing I'll mention, a side note in the concrete, I think that's very interesting. We've looked at that as well. We've tested the diffusion coefficient. Where that has come up is when regulatory agencies ask us to install soil gas monitoring probes between the barrier and the concrete, expecting not to see any VOCs in that annulus. And you will, because the concrete does have some resistance. And inevitably, when we get detections in those probes, whether it's methane or VOCs, the regulatory agency will go, oh, the barrier's failed, because we're seeing detectable levels of VOCs above the barrier. And so because of that, we did quite a bit of VOC diffusion and transmission testing on concrete, even as a function of the concrete water cement ratio, so we could quantify what concentrations you should see in the probes above the barrier. And I think that dovetails fairly well with the presentation we just heard.
Awesome. Thank you. Next question is for Yogi. Can we use this model in absence of pilot testing for new construction?
Yeah, actually, we have used this model for developing system curves. There are two things people need to design any system. One is the system curve. The other is like the fan curve or whatever, a curve for the ventilator turbine you develop, or whatever else, right? You're using to induce the vacuum. So yes, you essentially, this model is going to give out a system curve, and that every engineer uses to design to appropriately size the fan. So for new construction, which basically we are not able to go out and do pilot testing for new construction ahead of time, so you use this mathematical model to come up with the system curve. So the answer is yes.
Thank you. David, when you figured out that there was variability in ROI during these PFE tests, what did you end up doing about it? Did you have to do any post-construction additional risers? Just curious.
Yeah, that's a good question. I think one key takeaway from this is we looked at data for more than 50 buildings, and none of those had vacuum influence that was unacceptable. We were, in the end, able to get vacuum influence everywhere. And I think one thing that says is the design standard that we use, ANSI RCC 1000, and the riser spacing in there that we stick to is pretty conservative. So, if you have these systems and put in those risers at those frequencies, you've got a nice tight slab over everything. It creates a good vacuum influence. In some situations where we did have problem areas where we didn't get great readings, in each of those cases that I can think of, it was resolved by either improving the test port, removing water from it, or installing another test port just nearby. And it seems to be that was typically an issue. So none of these that we had to end up, putting in an additional riser. I can't think of one project historically that we've done where we did have to recommend to put in additional risers to address areas that couldn't be influenced.
That's good news. One question, I think this is for the group because it is a question that we receive a lot of, and I know we have a lot of experienced design engineers on this call. What is the criteria, or how do you decide the number of vent risers and the general spacing for a site? It's open to everyone. I know we might have a couple different opinions on this, so.
I can take a first crack because ours probably is the least, if you will, scientific. We kind of lean pretty heavily on the LA building spec for their methane systems, and their spec has one riser per 10,000 square feet. So we generally use that number and then round up, if you will. And we did a retrospective study just a couple of years ago looking at, some 40 different buildings, and trying to look at correlations between riser flow rate and different things. And like the tortuosity of the flow path for vapor to a riser, the thickness of the gravel layer, the size of the vent piping, et cetera, et cetera, et cetera. And that retrospective study indicated that the biggest, if you will, the best predictor of nice flow rates in the risers was just the number of risers. And so less so on the spacing. In our experience, you just shoehorn the risers in where you can find a spot that the architect, likes, and that works in terms of what you might have going on at the roof level and so on. So you don't have a lot of choices there. But you just, use the locations that you can get, design your vent piping around those locations, and you're kind of off to go. But again, it seems the biggest factor is the number of risers. So as over time we've hewed more and more closely to the one per 10,000 square feet and then rounded up, we've gotten better flow rates. But it's an inexact science. So that's my answer. Maybe some of my friends here have different.
I will jump onto that. That was the exact question that was raised when, in my mind, when I saw for a 800,000 square foot building, someone came up with 56 fans, and each fan controlling, I think, several vent risers. And I can't remember exactly how many vent risers, but a number of vent risers. So I'm like looking at this 800,000 square foot building. That's when the need for developing the model that I presented came in. Through modeling, we kind of reduced that to 15 fans with each fan controlling 2 vent risers, 30 vent risers, as opposed to some 120 vent risers or something like that, or more, actually. So the answer to your question is the ANSI guidance, at least to my knowledge, there is no engineering basis that is provided in the ANSI guidance of the size of the, whatever, that 10, 15, 12,000 square foot, you need 1 vent riser. They might have developed it using engineering basis, but that's not published, at least. That's not there. So using the modeling, I think you should use the model. That's how I'm going to answer that question. So just simply that I presented the case, 15 fans as opposed to 15 fans, 56 fans to 15 fans. That's the result of the model. So I would say use the model.
Yeah, just caveat, our study was just looking at completely passive venting systems, not active venting systems. And that's because we in the Bay Area very much avoid even active venting systems, just because of our air district requirements. They basically look at even just a simple wind turbine as being a mechanical device, and so therefore we fall under their regulations regarding air emissions, and that starts to require a fair amount of monitoring, which then becomes quite costly for our clients. And so pretty much we just go with passive venting systems. And of course, if you're looking at an 800,000 square foot warehouse, you're probably not putting it in the Bay Area. You're probably putting it in a little more friendly and, I suppose, reasonable location from a regulatory standpoint. And in which case, of course, mechanical venting system might make a whole lot more sense.
Consistent with what was said earlier, I see the Los Angeles Department of Building and Safety Guidelines referenced far more than anything else regarding the vent riser numbers and spacings and diameters, in part because it's so detailed. And what LADBS did to develop those back in it was the 90s and early 2000s, is they went out and measured soil gas flux rates at a number of projects within the city and took the site that had the highest rates, which happened to be Playa Vista, which is in an area of natural gas seepage above a gas storage reservoir, coincidentally. And then they took those flux rates and used them to design their guidelines with a maximum limiting overpressure in the ventilation blanket of 2 inches of water, which is why when you look at those guidelines, you've got 2 inches of water as a demarcation between a low risk site and a high risk site. That's where the 2 inches came from. So everything's designed, the lengths, the diameters, the spacing, to limit the pressure in the gravel ventilation blanket to 2 inches of water or less.
So I'd like to jump in here too. And I think the amount of airflow you need is really a function of what problem you're solving. When it's SSDS, the problem you're solving is that you don't have enough vacuum everywhere under the slab. So for that, calculate it the way Yogi would. Maybe you want to field verify it using David's methods with PFE test. If you're trying to ventilate, then it totally depends on the concentration of the VOCs you have subslab. If you have higher VOCs, you need a lot more air moving through. And if you want it to be a passive system and you have a lot of VOCs, passive might not do the trick. You might end up having to ventilate with a radon fan instead. But there are calculation methods you can use to figure out how much air to move based on the contamination presence. I presented on that at AVIP at the workshop last October. And if you know that amount, you can literally calculate what these risers are going to do and how far apart your piping should be and how big it should be if you want to. That's my approach. Other people who have been doing this a lot longer than I have better intuition about how that can work out. So if you're new at this, I'd recommend jumping in and trying to calculate it. But for that, you should probably get your hands on the AVIP presentations.
And I would mention that more vent risers or larger diameter vent risers are not necessarily beneficial under some scenarios. So we always run a model of every system, assuming it's going to be an active system, even though they're not intended to be. And then we always test them with a blower at the time of installation to make sure our head losses and our flow rates are consistent with our model. And then we remove the blower, but we know we can reinstall it quickly in the future if we were forced to. But 100% of our systems from the start are designed to operate passively.
Awesome. Well, thank you, everybody. My camera decided to stop working, so I was frozen for a second, and now I'm just blank. But I really do appreciate everyone taking the time to help inform the industry on some of the, I think, important factors as it relates to vapor intrusion mitigation. Michael, you have a lot of questions. I might find a way to send them to you, and we can try to figure out how to connect. There was a lot of questions related to the subslab concentrations and how that might vary versus thickness, as well as various types of concrete. So I don't know if you want to quickly delve into that, but that a lot of those questions were around the same idea.
Okay. Well, I'd be happy to, if they reach out to me, I'd be happy to answer the questions, or I can respond later.
Okay. Perfect. Well, again, thank you, everybody. We're a few minutes over, but I think it was valuable information in our Q&A process. If you're interested in learning more about ePro, please feel free to reach out to us. If you want to follow us on LinkedIn, we will be doing more webinars, bringing this kind of information out for people to learn more. And again, appreciate all of our presenters, Miriam for helping us put all of this together. And, thank you for sharing some of your knowledge with us, and have a great rest of the day. Thank you for all those who attended.
Thanks.
Thank you.